So in this video, we want to look at using the shell method to find a volume of revolution when we have a y-axis revolution. And down here I do have the formula for the shell method with a y-axis revolution for your convenience. I don't intend to refer to it, but it's there in case you need to refer to it. So the example says, use the shell method to find the volume of the solid of revolution formed by revolving the region bounded by the graphs of y equals x squared plus 1, y equal 1, x equals 0, x equal 1 about the y-axis. So y-axis revolution. So the region's going to be x squared plus 1. That's this guy right here, the parabola opening upwards. It says y equal to 1, which is this right here. And then x equals 0 really is just giving us this point of intersection of y equal 1 with the graph of x squared plus 1. And then x equal 1 would be this vertical line through here. So that region's going to establish this section right here that I have all in red. And we're doing a y-axis revolution. So notice when we revolve this region about the y-axis, this piece here is missing. So the shell method, because we're using the shell method and a y-axis revolution, we establish a representative rectangle of revolution. And that rectangle of revolution is going to be parallel to the axis of revolution, in this case the y-axis. And we would be revolving this rectangle about the y-axis in a circle in order to create an open cylinder, an empty cylinder. And so when I establish my representative rectangle, which is bounded by these two graphs, I want to notice right away that it has dx slices. That's the first thing I want to notice. And in the shell method formula, you always get 2 pi times radius. This p, which I really should have in there as a row of x, I haven't fixed that yet, so I feel bad about that. But that row is representing the radius of revolution. So we have 2 pi times radius, which is the circumference of revolution. It's just the circumference of the cylinder that we get when we revolve the representative rectangle about the y-axis. So I need to know the radius of revolution, which is just going to be the radius formed between the y-axis of revolution and the center of the representative rectangle of revolution. And what I want to notice is that the radius is actually just going to be the x coordinate, or the x distance to the center of that rectangle. This is a horizontal distance, so that radius is just x. So if I start to set up my formula, I'm going to say, hey, this is 2 pi times the radius. 2 pi times the radius is the circumference of revolution. And then I need to know the height of the cylinder that I'm revolving. I need to know that height as a function of x. And it's really going to be the difference if I label the y value here as y2 and the y value right here as y1. It's really just going to be the height of this cylinder is just going to be y2 minus y1, the difference between the two functions. The output difference between the two functions. But because I have dx slices, I need those described as functions of x. But we have that right here. The upper function, which I labeled as y2, is just x squared plus 1. And the lower function is just y equals 1. So the height, the distance from here to here, that height as a function of x is just going to be the upper function minus the lower function is just x squared. So I have 2 pi times radius times height as a function of x. So times height as a function of x times dx, the width of the cylinder or shell of revolution. And then we're integrating with respect to dx, so we're going to run over the x-axis from 0 to 1. So our x-axis bounds of integration. So we really see that we're just integrating 2 pi from 0 to 1 x cubed dx, which is an easy integration. This is going to be 2 pi times 1/4 x to the 4th from 0 to 1. So we really just get, when we evaluate this, so hopefully it's obvious that we just get a pi over 2 falling out of this calculation. We're going to get 1 cubed minus 0 cubed is 1 times 2 pi times 1/4 is just going to reduce to pi over 2. So the thing that you could think about is, well, could I use the shell method to do this? Could I have used the disk method from the previous homework? And the answer is yes. The disk method, we would need to work, because we have this missing region, our representative rectangles would need to run out to this line and then out to this line. We're going to get a difference of radii because we have to subtract off the missing region if we use the disk method. So if we were setting up the disk method would say, hey, you need to do pi r squared. And then notice that I've got dy slices sitting here. So it's going to be dy. And the disk method says, hey, it's a pi r squared type of thing because we're using solid disk or solid cylinders, and we need to calculate those volumes. So we get the outer radius, right? And the outer radius here, the distance from here to here is just x equal to 1. And so you'd get 1 minus, and then this inner radius right here, we need to know this inner radius. It is the x-coordinate, but we need the x-coordinate as a function of y. So I'd have to step up to my parabola, y equals x squared plus 1, and then we would need to solve this for x. So we would get x equal to subtracting 1 from both sides and then taking the square root of both sides and only the positive square root because we don't need that part of the parabola. We would get an inner radius of the square root of y minus 1. So the disk method would say, hey, you have to use the washer method, so you're subtracting off the piece you don't need. So take the outer radius squared minus the inner radius squared, the part that you're subtracting off, and then it's dy slices, so we'll need to run it from 1 to 2. So that's what it would look like if we set up the disk method. So with the disk method, we'd have to do some simplifying. 1 squared minus parentheses y minus 1 dy. And simplifying that a little bit more, we'd get pi times 1 minus y plus 1 is 2 minus y dy. And so we'd get pi times integrate. So this would be twice y minus integrate y. We get 1/2 y squared evaluated from, not from 0 to 1, from 1 to 2, from 1 to 2 on the y-axis, not from 0 to 1, from 1 to 2. I have 0 to 1 over here, so that's what's in my head. So you're doing this from 1 to 2, and then you'd need to plug the pieces in. So we'd get upper bound of integration, 2 times 2 is 4, minus 2 squared is 4 divided by 2 is 2, minus parentheses 2 times 1 is 2, minus 1/2 of 1 squared is 1/2. And then we'd simplify, we'd get 4 minus 2 is 0, minus is plus 1 times 1/2. So we'd wind up getting the pi over 2. And what you want to notice here is that the disk method calculation, even though probably conceptually the disk method is a little bit harder to wrap our heads around and to understand, the disk method is actually substantially easier than the shell method is. And in general, that's going to be what the consideration is. When you look at a volume of revolution, you're asking yourself the question, which method is going to be easier to use, the disk method or the shell method? And as we'll see in a subsequent video, sometimes one method is possible when the other is not.